Wote jambo nangadef mbote. Akwaba guys, if you are joining me in this video, my name is Marcelin Inidabo. I am an African from Senegal, a PhD on control systems, consultant in engineering industry, and an independent researcher. So, I want to present you some concepts from which I go to state in the previous videos that it is possible to compute the time response for any given second order system that it can be. Okay, this is what I will do in this video. But remember that I have talked about first order systems, okay, and giving in a first video the different fundamental laws for what is an autonomous system, and also the step response of a first order system. I also talk about a formula that I called an ISO time constant formula because it allows you to compute according to the time response at any fixed percentage of the output during the transient or at any rise or fall time during the transient also, the time constant. So you can compute the time constant of your system only when you fix yourself in a 1 point for a first order system, not necessarily at 63% for an initial response, for example. You can choose 20% and you will be able to compute your time response. Sorry. And then also, in a third video, I have introduced a new criteria, a new paradigm to identify a first order dynamical system. Okay, from there you can see that you just compute a specific ratio of time responses at a very precise points, percentages of the output according to initial condition, or relative output according to relative initial condition, and you will find what you are looking for. In a fourth video, I have presented and shared with you uh, a table of design of first order systems according to the performances, the temporal performances that you want to reach. If you want to reach a time response of 95% at a fixed value, like 1 second, you can derive the time constant related to that. The formula is known. Or if you want a time response at 98%, you can derive the time constant, derive also the cutoff pulsation and also the cutoff frequency. Okay, and then from there you simulate your system, and finally you check the consequences of that choice on the other values like time response at 80%, like rise time between 5 and 95%, etc. You can do all this. For second order systems, I have started presenting the fact that it is possible to compute the time response of any given second order system. Okay. Might they have the damping ratio that is less than 1, that is equal to 1, or greater than 1, meaning that respectively, when they have an underdamped, critically damped, or overdamped system. Okay? So I argue that, and I present that videos, and I show that it is possible thanks to a new vision, a new paradigm, and new definitions that I have introduced, is that for any given second order system, there is only one time constant that is equal to tau equals 1 divided by the damping ratio multiplied by the natural pulsation. This is a new definition that I have introduced for dynamical systems of second order. Traditional control systems do not teach this. They teach that if you consider different cases I have enumerated, meaning that for the underdamped, overdamped, and critically damped, you have different time constants. Sometimes you have double time constant, for example, for critically damped. You have complex conjugated, okay, for the underdamped, and for the overdamped, you have two real uh, roots, okay, for two real-time constants for your system. But in my view, and what I have introduced in this new paradigm, is that there is only one time constant. So how I get to that result, this is what I want to share with you now. So if you are ready, let's go. If we consider a dynamical system of second order, you have it written like this, okay, as I talked about this during the previous videos, where you have B over A0, this value is again static gain. This value A1 over A0, we will see how we call it. This is A2 over A0. So now, this is only for second order systems. Let's consider now a greater order, okay, superior order to order 2. I mean, we take order n, for example, and then we write our equation, differential equation like this, where the A0 can be multiplied here, and then you don't have the denominator. But for commodity, let's just divide, as it is written here, all the expression by A0. And then what you have, you recognize this is a static, here the static gain. So it is multiplied by the input. Here is the output S, the first derivative, second derivative, until to order n derivative, okay? And then if you just focus here for the first order system, for example, you stop at the first derivative here. In the known definition, what is very well known is that A1 over A0 is what we call in control systems time constant of our system. If you check it deeply, you will see that the equation of dimensions will imply that the units that you have here, for example, for this output, should be the same unit for this expression, because if you have to add values, you should add values of the same unit. Therefore, the ds here is a conservation, because only the difference between 2 points, 2 and 1, for example, of this output, and then according to their corresponding time, and then here the ds at the numerator will keep the same unit as this expression here. So the A1 over A0, its unit is seconds. So if you take seconds, multiply by the second here, so you will have the conservation of the unit. Let's say meter, for example, here, and then you will have meter here, and this expression as whatever you can consider as inputs that can fulfill this law. This expression will be in the same unit as this expression, because B over A0 will take the same expression, okay? And then, so you can see that this is what we call a time constant. But the d of t here, okay, we can call also this expression as a linear temporal step, okay? Because I consider that when every dynamical system is moving, there is an internal characteristic that is a time constant. Okay, this is my paradigm. And the time constant that you have here is multiplying a line. This is why I call it a linear temporal step. And when the system is moving, every position that the system can reach, it reaches after a multiple of the time constant for a first order system, okay? And I call it also constant of the temporal line. Why? Because it is multiplying this expression here. In terms of units, they simplify themselves. Okay? Themselves. They simplify each other. If we go, so this is what you have here, A1 over A0 is a natural time constant, okay, or the time constant, also for a first order system. If you consider that you have just a second order system, what you have here, the static gain will not move. And then here, as you multiply by the line, by the temporal line, what you have here is it is a natural time constant. This is why I call it natural, because if you divide here, you will see that these terms multiply this line, and then it is naturally what you have. Okay, I think this is clear. By definition, I call it like that. This one, the A2 over A0, remember that we just stop here for the moment, considering a second order system. The surface time step, this is how I call it, because the expression here is, if you check the unit, it will be second times a second, and then it will give you a second square, and I consider that that is a surface of time. Okay, if you see it in another way. And this surface of time will impose to keep the same unit here, that the A2 over A0, the unit is second square. Okay, and then, so I call it also constant of the square of time here, because it multiplies here the square of time, and they simplify, and you can keep, thanks to that, the units that you have here. Okay. I call it also constant of the temporal surface. Okay, so these kind of expressions, I don't know, maybe they have been introduced in physics for a long time, and finally people leave them away and continue just with the expressions more simple. I don't know, but if it is not the case, I am the first person to introduce this kind of expressions in the physics, and particularly in control systems. So now, if we go further, when we consider the order n, by stating, okay, by checking the things under the same angle, okay, under the same paradigm, also what we can see is an over a0 should have the same unit as dt of n, meaning that second to the power n. When they simplify, it helps us to keep the same unit as the s of t here, and you have an homogeneous equation in terms of unit, in terms of dimension. And then this, I call it, this A1 over A0, I call it the n-order hypersurface temporal step, because if the system is moving as from the same philosophy, from the same paradigm, I consider that the system will do steps. When the order is n, so it is greater than 3, because we could consider the order 3 here, and for that we would be talking about the constant of the temporal volume, not temporal surface, because for A3 divided by A0, we would be with seconds to the power 3, so a cubic seconds, okay? So now, a constant of the temporal hypersurface of order n is here, right? And then, why people talk about static gain in control systems? It is because all this expression from here, from the first derivative to the nth derivative here, when we reach a permanent state of the system, meaning that no variation, no more variation, or very teeny variation, we consider as that they are equal to 0, there are no variations. So the only remaining expression will be s of t equal b over a0 times e of t. And then if you divide s of t, the output, by the input, you will get a constant. And as there is no more variations, so the system is now moving statically, no variations. This is why we talk about the static gain that you have here. So now let's go, as you see, for the expression, let's apply now what we have defined to here. So we just stop at the second order system. And then you recognize here, as I told you, that the A1 over A0 is the natural time constant. How I will call this? I will call this a constant of surface. Okay? I will call it the constant of surface of time. Surface time. Let me just check. Surface time step, for example, or constant of the square of time. Okay, this is how I call it, because it is multiplying here the inverse of the square of seconds. Okay, so the unit here is second square. When you have both, what you do, you divide the tau and this tau by tau and this n, and then it will give you A2 over A0 multiplied by A0 over A1, and then the A0s will simplify themselves. You just keep A2 over A1. This is what I define as a relative time constant. So if you hear on another videos, what is the relative time constant? It is this one. Okay, and this relative time constant that you have here is very important for us for the next step. This is a static gain, as you have seen. Okay, here, from these definitions, we rewrite this expression here. It gives us tau and this tau by the second derivative plus tau and this n by the first derivative plus s of t equals static gain multiplied by the input. Most of the time in control systems, people write second order systems like this one, okay, or sometimes they just multiply by omega n square everywhere. But in order to fit with this expression and to do the identification of parameters in front of the others, we have this expression, and then we have the tau tau that is equal to A2 to A0, that is also equal to 1 over omega n square here. The tau n is equal to A1 over A0, that is equal to 2c over omega n. By using this expression of tau r, you can see that you just multiply this by the inverse of tau n, and then omega n will be simplified. This 2c will go under, and then you have 1 over 2c omega n. This is the relative time constant, which is very important. And it is when you double it, you get what I define as the time constant, the only time constant of our dynamical system. And this is equal to 1 over c omega n. Okay, the static gain is what you have here. So what you should keep in mind is that this, in my paradigm, is the only time constant of our dynamical system of second order. There is no other time constant. Even if you resolve as in traditional control, as I present in the beginning, yes, the traditional control system I have studied also says that you have the different time constants according to the damping ratio that you should calculate. Okay. Let me say it again. If you have the damping ratio less than 1, so you have two complex conjugated time constants. If you have the damping ratio equal to 1, you have double time constants. If you have the last one, that is the system that is overdamped, so damping ratio greater than 1, you have two real time constants. Okay. In this paradigm, I defined one time constant for our second order system. So what is the impact of this? We are going to see it. Let's move now. So as I was describing during the last videos, I say to you that this is possible to compute for any given damping ratio, the time response at any given percentage of the initial condition or of the final value. Okay, if you are in a step response, if you have a step response. If we look at this expression, what we see is that in this case, the solution of our system is function. So here, just consider that we are working with an autonomous system. okay, meaning that the B over A0, B is equal to 0. So no input, okay? We don't have an input here. What we have is just that we have the differential equation. The initial condition here is different from 0, the initial condition of the variable. But the initial condition of the derivative is equal to 0 to simplify the expression. So we have this expression here. Okay, so as you can see, the SDP is the initial condition of S. You will see it everywhere here, and it is multiplied by a function of time. This function of time can be divided into two parts. One part with an exponential and the other part with a given function. So in this case, we can see that we are living, the system is living in a trigonometric world, trigonometric circular world, because we have the functions in trigonometry as we know. So here we apply the theorema. That is a theorema of the African priest, because when we talk about Pythagoras, Pythagoras have studied 22 years in Africa, and the priest taught him, and the African priest, the African black priests, knew his theorem 1,000 years before he went to life. Okay. So when I come back here, when you have a trigonometric function that is moving here according to time, if you envelope this function with the exponential for a stable system, the exponential will push the system to the equilibrium. When you see here, or in this case where c is equal to 1, you have this expression, and then the function is living on a line, a given line, so this is an affine function, okay? And you always have the exponential. So pay attention to the exponential. The difference between the two is the same. There is no difference because we just permute this TD with this t according to this expression that you have here. For the last one, for the last expression that we have here, we can see that the form of writing is exactly the same with the first one. Except that we are living, the system is living in a hyperbolic world here. Why? This is why you have cotangent hyperbolic here. This is why you have hyperbolic sinus here. Okay? And the expression under the root, to be well defined, we put c squared minus 1 here. As you can see, this is a positive result. If you put this at square and then you make the transposition of the 1 here in this part, you will have minus 1, and then it is greater than 0, so you can put the square root. Very important to understand that most of the time in the literature in control systems, this expression is not written like this. It is written in a different manner as a sum of exponentials, only like that. So if you keep this expression, you check it, you keep this expression, you check it, and then you leave the other expression, you will not be able to see the same character for this exponential function that you have here. They are the same, okay? And what I want to say to you here is that this exponential function, to observe it, to be able to observe it, you should first write this expression in this way. There is no another way to write it such that you will be able to see how they look like, okay? Because they are identical. And then I want to say that it is also through a contemplation that you can find this kind of result, a deep observation that you can see finally that the time constant of this, of the second order system is only this one. This kind of result, you cannot get it in excitation. You have to do something, you are rushing, shouting. I mean, when you take your time to think, somebody says to you, you are lazy. It's not possible to work in this kind of environment of tergiversation. I mean, In French, we say tergiversation et prestidigitation. You cannot get the result. You cannot. Because this excitation world, everybody is running everywhere. So wisdom says that when the water is stable, when the spirit is stable, okay, at that moment you can have a very great ideas that came to fill your spirit. Okay, this is how it goes. But if you just take your time, you put the line of codes and you are running faster than Mach 21. I mean, good luck for you. Okay, this was just a parenthesis to make a comment on this kind of result. It's very important. The way you write results, you can see it here. It is because I have changed the way of writing these results, this last one. First step. Second step, I have observed deeply. So I have done a contemplation of these results. Okay. This is why I could see that they are together. And I remember also another expression. Which one? I remember that for a first order system, it is written like this. And we define a time constant for a first order system like this. And then look at this expression of exponential. Look at this. You have SDP here. You have SD here. That are the initial conditions that you have everywhere. And then you have a function multiplied by an exponential function. Here, there is no function. There is directly an exponential. Or we can consider that the function of t here is only equal to 1. It's a constant. Okay? And then when you check the things like that, what you have here, you have the expression here related to the exponential is minus t minus td over tau. If you check minus t minus td over a given tau, let's call it tau s, for example, if you say that this expression is equal to t minus td over tau, you simplify, and then finally you have xc times omega n equals 1 over tau. Therefore, tau is equal to 1 over xc omega n, what you can see here. This is why, going from this, okay, you can see that the only time constant of a second order system is this one in reality. Because you can write it in this manner, in this vision, there is no other way, okay? And then the role of convergence is played by this one. Okay, so I hope this is clear for you, the way I bring it. So this is how I derive the fact that there is only one time constant for second order systems that can be written like this. Okay, and now we will see in the next video how to be able to compute the time response of any given second order for any given damping ratio, okay, time response, rise time, etc., to any other systems. And we will discuss other subjects also to show you that there are some results that are advanced today in control. Maybe we just need more clarification, I think. Okay, according to what I have observed. So, all these results, as I told you, are synthesized in this book. I am the author of this book. This is a French version, so the English version is coming. And both of them, they are coming. And it is just written, this is the title, Dynamical Systems, New Vision, New Paradigm, New Methods for characterization, identification, design, and control systems. So yes, of course, because I talk about identification, going from this paradigm, I will present you how to make identification of a second order system. And from that identification, how it is possible to derive even the damping ratio and the natural pulsation of our system. So I hope that this video, you have enjoyed it. And then I want to thank you very much for following this. Please like and share and join the channel if you want to support our job. And I want to thank you again very much. And I hope that we will be able to, you will be able to join very soon another videos and to learn again about some other visions in control systems. So I hope this video will contribute to help different people on their researches, on their calculations, their simulations, etc. Again, thank you very much. I say to you all, Jërëjëf, that is thank you in Wolof, a language of West Africa, deeply linked to pharaonic language in Egypt. Thank you very, very much, and we talk very soon.